We're one of those black swan type things that no one expected and no one really saw coming. And while it might seem like energy transition is struggling a little bit, don't give up hope.
Greetings, Earthlings, and welcome back to Earthlings 2.0, the show where we imagine how we can be better versions of ourselves and build a collective future we actually want to live in. Today's topic continues two side quests that we've been pursuing to understand the opportunities presented to us surrounding renewable e-fuels and hydrogen power. Except today's show looks at the alignment of plasmonics, nanotechnology, and light to produce those same low carbon intensity chemicals, but at a cost that could swiftly reach parity with conventional e-fuels. But before we beam up our guests to give us a Mr. Wizard level explanation of their revolutionary photoreactor technology, and I don't say revolutionary very much, and I'm not being hyperbolic there. It is a one of a kind tech. It's like nothing else, and it really has the potential to change our timeline for us, if I may be so bold. So before we get there, I'm your host, Lisa Ann Pinkerton. I'm the CEO of the award-winning public relations firm Technica Communications and the founder of Women in Clean Tech and Sustainability. And before I built those organizations, I was an award-winning environmental science reporter for NPR and PBS. And I want to thank all of you for joining us today, to being a listener, whether this is your first time here or your third or 15th time here. Welcome. Thank you for being with us. If you want to give back to the show, you can share this podcast with one of your friends. The next time you're talking podcasts, go ahead and shoot them over your favorite episode. That is single-handedly the best way to support the work we're doing here and help us continue it. If you've already done that, you are welcome to do a few more things. You can be a power listener with us if you'd like. That's joining our newsletter, and we'll only hit you up once a month to give you a rundown on what's been happening on the show. You could take our listener survey and help us better understand you and therefore bring you content that is more tailored to your interests. And also, you could join our Patreon page and become a member of our community more specifically and get extended episodes from the interviews that we have here today. And I want to thank Resource Labs for having us on the network. Today, the vast majority of chemicals and liquid fuels have carbon emissions deeply embedded in their manufacturing. That's why things like e-fuels, synthetic fuels, green hydrogen are gearing up to change that. However, they're also typically expected to be more expensive than conventional fuels. We've called that the green premium in past episodes. However, Syzygy Plasmonics is shedding light on a new way of creating these chemicals, methanol and hydrogen, by using a proprietary photocatalyst that replaces combustion in the manufacturing process and eliminates the carbon emissions associated with powering chemical manufacturing. Their solution goes all the way down to the nanoparticle scale, and it leverages the science of how light and metal react to create this new solution. But I am far from an expert here, so let me stop right there and introduce one of the Earthlings behind Syzygy Plasmonics, Trevor Best. He's the co-founder and CEO of the company, and before catalyzing this new branch of our timeline, he worked in the oil and gas sector at the oil field services company Baker Hughes, which I'm sure gives him a really good perspective on his customer base at Syzygy. Our conversation went very long and it was very detailed. So, if you want the full download on how light driven chemistry can make our future more sustainable and cost efficient, click on the show notes and set yourself up as a member of our Patreon, and you can listen to the entire episode. Being a word nerd myself, I kicked off our conversation with a question around this word, Syzygy.
So syzygy is a really interesting word, but we do really serious science. So the word syzygy is the straight line configuration of three gravitational bodies. A perfect example of this is an eclipse, where the sun, the moon, and the earth line up in a straight line. For my company, what it means is the alignment of three things that are shaping the future, and those are energy, technology, and sustainability. And where those three things line up, you get Syzygy.
I'm putting that in my $10 words column for usage.
If you can land it on like Scrabble, a triple letter and triple word score, you absolutely destroy.
Oh, good point. Mental note. All right, thank you. And the next thing I want to really get into before we get into your technology is the pain that you're solving when it comes to industrial decarbonization. What is the industry experiencing today?
So, when we're talking about chemicals and these are things like fuels, fertilizer, other raw materials that make the products that we use every day. These are traditionally made in gigantic chemical plants or refineries, and at the heart of those chemical plants and refineries, you will find an enormous chemical reactor that is powered by combustion of fossil fuel. So they burn some kind of fuel source like natural gas to produce the heat and pressure needed to operate these chemical reactors. And unfortunately, that combustion results in more than 2 gigatons of CO2 every single year. So as these industries are trying to transition into low carbon molecules and clean up their operations, this is proving to be one of what they call the hard to abate sectors. It is very difficult to eliminate combustion from these chemical manufacturing processes, and that just so happens to be exactly what we do. And if you'd like me to go into that, I'm happy to tell you.
Yes, please. Natural segue. Thank you.
Yeah, so how Syzygy eliminates combustion from the chemical manufacturing industry is because we have created a completely new type of chemical reactor. Our chemical reactor is fundamentally different than every other chemical reactor on the planet. It is based off of a field of science called plasmonic photocatalysis that has been pioneered by Rice University over the past couple decades. And using this process, we actually drive our chemical reactor with light from the world's most efficient artificial light sources, and we use that light to energize the world's most stable and active photocatalyst, which uses light to drive chemical reactions. And this allows us to create a completely novel type of product, which is a light and renewable electricity driven chemical reactor that can help to decarbonize this sector.
Wow. Okay, so there's a lot to unpack there. Let's start at the beginning. Uh, I understand that some of this technology, like you said, had been developed from Rice University, probably going back as far as the 70s. But my assumption is it hadn't really progressed. And then you all came along, and it sounds like you created a turning point for this technology. Can you explain a little bit about what you did?
Absolutely. So, getting into some of the history of photocatalysis, it was first started in Japan in the 1970s, where they were doing photocatalytic water splitting using a material called titanium dioxide. This is a semiconductor type material, and so we would call this a semiconductor type photocatalyst. There were some fundamental challenges, and unfortunately, titanium dioxide is not a great catalyst, so it doesn't absorb, a large spectrum of light. It's really only active against UV. And then finally, titanium dioxide isn't an especially good catalyst either. So in industry, to do different types of chemical reactions, they have lots of different catalysts. And so with titanium dioxide, you had something that was not that great at using light and not that great at driving chemistry. So in the 1980s, a pair of professors, Professor Naomi Hollis and Peter Nordlander, started going down this rabbit hole of a field of science called nanophotonics and ultimately plasmonics. And nanophotonics is the interaction of light and matter at the nanoscales, and plasmonics is a specific subset of this field where a few materials, the plasmonic materials, when you hit them with light, they absorb all of that light and they transfer it into the electrons on the outside of the materials. And in 2016, being researchers, they were very curious and they said, I wonder what would happen if we started combining these, near perfect light harvesting nanoparticles with traditional catalysts used in industry today. So they started taking some of the catalyst materials that are used in refineries and chemical plants today and embedding them into these plasmonic nanoparticles. And the results they saw were astounding. So when we look at like decades of research, this is a new field of this photocatalysis research, specifically plasmonic photocatalysis, that has really only entered the fray in the past couple years. The fundamental physics behind how our catalyst works wasn't understood and published academically until 2016. So this is like at the
Wow.
absolute bleeding edge of human knowledge.
So now that we've got all of that, can you explain for us step by step how your technology works?
Yeah, so for our technology, we have a cell-based technology where we have our Rigel reactor cells. Rigel is the name of a very bright star in the Orion constellation, and being light-driven and Syzygy being an astronomy type word, we love things from space. So of course we named the reactor Rigel. Uh, a single Rigel cell is about the size of me. So it's about 6 feet tall and about 2.5 feet wide. And it is composed of a quartz tube that holds our catalyst. And then you sink a very powerful light source into that quartz tube and you illuminate the catalyst using that light source. So as a cell-based technology, we scale up by mass manufacturing these cells and putting them into modules. So other similar technologies that you might be familiar with are things like batteries, where you put a bunch of battery cells into a battery pack. Like if you open up the battery inside your Tesla, you will find thousands of little cells. So that's how our technology scales. We make the base cells and then we put however many we need into a cell stack to achieve scale.
What does the cell look like? You can't see into it, I assume, because you're pushing light into it, so you wouldn't want that light to escape, right?
What does it look like? It's a little hard to describe. I have heard that our technology looks like a flux capacitor from Back to the Future or a warp core from Star Trek. And essentially you have a glass reactor that is illuminated from the inside, and as you turn the light on, it lights up pretty brightly. Whenever we put it into industrial applications, we put it inside a pressure vessel, so it looks a lot less cool.
It looks like it's just like a glowing orange tube with a lot of industrial components and wires and things coming off the top, and then you have a big metal base at the bottom. And you say it's about the size. How tall is it?
So I like to joke that it is a Trevor-sized reactor cell, so it's about 6 feet tall and about 2.5 feet in diameter.
So now that we've got our heads around that, help me understand what types of reactions you're able to perform and then how industries are going to benefit from these reactions.
So we can do a couple different reactions today. It's a platform technology. We have two pathways that we're working on that go to hydrogen, and we have another pathway where we're able to take in greenhouse gases and turn those back into useful products like fuel. So the first hydrogen pathway that I want to talk about is ammonia e-cracking, where we are bringing in ammonia and we are cracking it to make hydrogen and nitrogen. This reaction is really interesting because it enables the import and export of green hydrogens, very similar to like LNG. And we're essentially like the LNG regas for the hydrogen ammonia value chain. The second reaction is our blue hydrogen pathway. So this is our e-reforming reactor. And in that, you're feeding in methane and water, and you're creating a mixture of hydrogen and CO2 on the back end. So because we eliminate combustion, we eliminate about 40% of the emissions that are usually associated with this process. So there's an immediate emissions reduction, and then the CO2 that is made is much more concentrated and very easy to do carbon capture and utilization on. And the final pathway is, our CO2 or greenhouse gas to fuels pathway. And in this one, we are taking in a mixture of water, CO2, and methane, and we're turning those into a syngas that has a 2-to-1 ratio. And at that ratio, you can then feed that syngas into a Fischer-Tropsch unit or a methanol synthesis unit and turn it into some kind of liquid fuel. And this is great when you have, anthropogenic methane, like from landfills or, anaerobic digesters tied to dairy farms. So like landfill gas or biogas, or if you are working in a chemical plant or refinery and you have a stream of CO2 or methane that you don't want going into the atmosphere and you want to turn that into more product, we can help decarbonize that way as well.
And so, speaking of all of this, you have recently demonstrated your CO2 to fuel solution with RTI International. And I was hoping you could share us a little bit about what that project is and what some of the outcomes have been so far.
Yeah, so in that project, we had two public sponsors and one that didn't get announced. So the two public ones were Equinor and Sumitomo, and then there was another international oil and gas company that was sponsoring that. And in that project, we took in methane and CO2, processed it through our reactors into syngas, and then fed that syngas into RTIs, which is a Research Triangle Institute out of Raleigh, Durham, North Carolina. We fed it into their Fischer-Tropsch unit and turned it all the way into fuel. This project helped prove out a couple different things for us. First off, this was the first time we've taken our technology to a third-party site and installed it and operated it. So it showed like as a company we had hit that level of maturity where we were ready to go operate at other people's sites. It also proved that our technology could be integrated into upstream and downstream components. And in this, we talk about many cells working together to achieve scale. This was the first project where we tied in many cells together. And so this was a 3-cell project where we had 3 cells operating in parallel. And ultimately, we were able to make synthetic fuel. And so, like, this is actually a jug of our syn fuel that I keep in my office as a memento from that project.
Well, you're holding up a glass jar with clear liquid in it, um, and it's got all kinds of hazard notes on it, which you need when you have a clear jar of
When you've
liquid.
got a jar of syn crude in your office, it's good to let people know that they shouldn't take a swig of it.
Exactly. Exactly. Okay, so what other milestones have you achieved recently that are showing the company's technology is getting ready to commercially scale?
Yeah, so there's a number of activities that we've been doing that show that we're ready to commercially scale. I'll split them up into a couple different areas. Another one is our demonstration plant that we have in the backyard of our facility here in Pearland. We're operating a full-size Rigel reactor cell for ammonia cracking and soon to be reforming reactions as well. We have built a very similar. We've worked with our partner to build a very similar setup in Ulsan, South Korea for another field trial. So another deployment at a customer site, where we prove that we can operate our technology against the metrics that we promise them. And we've also been working on gaining customer traction and have been signing up project participants in a demonstration plant to deploy these at what we call small commercial scale. So when you think about like a chemical plant, it's like a giant $1 billion facility. We're planning out pretty large, like double-digit millions projects for landfill gas to fuel, biogas to fuel, and ammonia cracking to prove out to potential future customers that we're ready to take that final step into large-scale deployment. The timeline for the demo project is probably over the next 2 years. And the timeline for the true large scale deployments is probably like late 2026, where those start to get sanctioned coming online in like 27.
One thing we haven't talked about When you're, what's the emissions profile of some of the fuel? Like, say you're creating some kind of e-fuel for aviation. There's still an emission, the carbon emission profile when once you combust that fuel in the engine.
So that is a fantastic question, and that is probably the single most important question you can ask anyone. And when we think about the emissions profile, I think about it in terms of what's called a life cycle assessment. So you look at your feedstock and where that's coming from and what the carbon intensity is. You look at your process and what that is and any emissions generated there. You look at any like post processing and transportation, like how do you get it to market, and any emissions generated there. And then finally, use. So if you're like putting a fuel into a vehicle and you're burning it and it's created emissions, and so you got to look at the whole value chain from start to finish. And we're getting a lot more people savvy with that, and the government is starting to look into this quite a bit. So for Syzygy in our processes, like if we're talking about either hydrogen or e-fuel, we offer a range. And so, on one end of the range, you have lower carbon, where we have options that can reduce the carbon intensity by, like, let's say half, and those are less expensive, all the way through options that are very carbon negative. And I'll give you some examples of those. So, like if we're looking at e-fuel, we feed in CO2 and methane into our process. If we're using biogenic CO2, which is negative, and we're using fossil methane, which is positive, the resulting end product has about half the carbon intensity of a normal fuel. So it's a 50% reduction and can be very cheap. So whenever I talk about being able to hit parity, same price as normal fuel, but half the carbon intensity, it's not bad. I'm happy with it. We have another option where we can actually get to like carbon negative, where we take in like landfill gas and turn that into sustainable aviation fuel. And landfill gas is a lower carbon intensity, and altogether across that process can be carbon negative, and then but just barely. Or we can go all the way from dairy gas, which according to the United States and how we do our carbon accounting, is incredibly carbon negative. And so the resulting product, even after burned, is very, very carbon negative because you're preventing the methane emissions from that dairy farm. So, but that one's the most expensive. And so, depending on our customers and what they want, we can offer a, very cost competitive carbon reduction all the way through. If they want a very intensely carbon negative product, we can get there as well.
What's the cost difference between the solution you're bringing to market compared to other options that the industry might have?
Yeah, so given that we have multiple different pathways, this can be a pretty complicated answer. So like that changes if we're talking about like ammonia cracking in Europe or Korea or Japan. Each one of those, has a different cost profile, different for blue hydrogen or e-fuels. But in general, what we're seeing is the potential for a 20 to 40% cost reduction versus other clean technologies. So like if you've made the decision that you're going to clean up and start to decarbonize your processes, we will offer be able to offer at least a 20% cost reduction, and in some good scenarios up to 40%. And in some cases, under the right conditions, we can actually hit parity with fully carbonized fossil alternatives. So not only do we eliminate the emissions, but if we work in the right areas, we can actually hit parity and compete head to head against fossil alternatives, which is a very rare thing for clean tech to be able to say.
Break that down for me. How are you able to get such cost savings through your solution?
So it all depends on like a sensitivity analysis, and the end product. So if we're like going to jet fuel, then we look at the cost of jet fuel in the industry today. We look at the cost of the inputs, and if we are able to like source our biogas or our landfill gas at the right price, and we can actually get a very low price because we don't need much cleanup on that. We can essentially take the raw landfill gas that hasn't been processed and feed it into our reactor. And if we can get electricity at the right price, let's say around 6 cents or so per kilowatt hour, which is very doable, then yeah, we can start to get close to parity. But it is definitely not everywhere that that's possible. If you go out into California and the average electricity price is like 17 cents, it's going to be pretty hard to hit parity there. But in other parts of the U.S., much easier. And for different parts of the world, like if we're comparing, hydrogen in Japan, our ammonia cracking technology can compete head to head on hydrogen prices in Japan today. So yeah, that's another way of looking at it.
Okay, so it sounds like you're eliminating some steps, which reduces cost. You're able to select locations where there is a lower cost of electricity. Also, you're utilizing renewable energy, which is typically cheaper than fossil fuel based energy. And so all of these different pieces, when combined together, help get you to a lower price, in addition to the just the innovation and advancement from your technology itself.
Bingo, you got it. It all comes in together. One thing I like to note is that I think it takes a village to actually decarbonize the planet. There is no single solution that is a panacea and solves all problems everywhere. But there's probably enough silver buckshot to get the job done, and we we're more than one of those BBs, talking about the different pathways. We have a couple different solutions all together for the end molecules we're targeting, like hydrogen, e-fuels. We have about 60 to 70% global applicability. So in about 60 to 70% of geographies, we will have a very strong value proposition when we look at like the price of feed and power, et cetera.
So I'm curious to know, what's the appetite of the broader chemical industry and fueling industry to adopt either a solution like yours or another one to decarbonize their operations?
So we are getting some, pretty strong traction that I mentioned. So to just like list out the companies that have invested in Syzygy, and this is like a really good way of them showing like support, like they're interested in the tech, they want to see it, come to market. We have gotten investment from and are exploring opportunities with, BP, Chevron, Aramco, Equinor, Toyota, Sumitomo Corporation, Latte Chemical, Mitsubishi Heavy Industries, Pan American Energy, which is the largest energy company in South America, and Zeon Chemical Corporation. So lots and lots of industry traction. What's the appetite? Uh, that is an interesting question because chemicals and fuels and things like this are a pretty brutal industry, and it just all comes down to economics. If you can give them a positive IRR on their, so it's internal rate of return, on their projects, and the hurdle rate for a lot of them it gets close to like 20%. If you can meet that, then like they will buy. The project makes sense, and they have a huge appetite for clean tech that has good economics.
It always comes down to economics, and but I can also sense that all these companies that you rattled off, there is social pressure out there for them to decarbonize. And they, obviously the writing is on the wall, and they don't want to end up like, I don't know.
They don't want to be Kodak.
They don't exactly. They don't want to be Kodak. And so I can see that there's an appetite, but it has to make economic sense because it is a very brutal market out there.
What I think is going to happen over the next couple of years is right now, a lot of those companies have placed a lot of bets into a lot of different potential pathways. And so they are actively trying to figure out what will work where. If you remember, I said there is no silver bullet. So they don't believe that anything is going to solve all their problems. So they're testing different things out to figure out where they can apply different technologies and how to solve their problems in different geographies under different conditions. My guess is that a number of demonstration projects will be, operating and coming online through the 2026 time period, and then we're going to see the real energy transition kick in like 2027 and 2028. Once they have enough understanding of what technologies are out there, how to make them economic, And I think that companies will start to commit more and more resources to decarbonizing because they do feel that social pressure. It is not going away anytime soon. And they're seeing more and more things like, impact and activist investors like taking positions on boards, which has happened, a couple times recently. They're seeing governments, come in with a little bit more teeth. That is only increasing as time goes on.
Yeah, yeah. And I think the key for all this is going to be because a lot of the carbon from that I've heard, a lot of the carbon emissions that are embedded within the transportation sector may not be in as much in the production of that fuel, but in the transport of that fuel. And so if we could get to a future where the vessels are running off of a e-fuel and also transporting e-fuel, then we know we've reached a place of achievement that we've been looking for. So when do you think something like that might happen?
I don't know how much stock I'd put in crystal balls right now. I think if we went back to 2019 and tried to predict what the next 5 years would look like, it would have been a tough proposition. So I will say that the only thing that I am certain of is that uncertainty is going to increase in the future. I think with climate change, we're going to see a lot more variability across supply chains as there's more and more weather events. I think, there's going to be probably more geopolitical instability. And so the only certainty is uncertainty. On that note, like for fun, if I was going to make a prediction, there is a lot of societal pressure to decarbonize. There is a lot of societal pressure to control costs. Going back to the benefits of a drop-in replacement, I think that we're going to see, just skyrocketing demand for e-fuels for all segments. I think, definitely for sustainable aviation fuel to cover aviation because there is no good alternative. But also, we're seeing growing demand for, renewable diesel or biodiesel for shipping, for trucking, and I wouldn't be surprised if we even start to see it for consumer applications where you can potentially get a low carbon fuel at the gas station. Now that hasn't been done successfully to date, but given what we're seeing with people like making changing their food choices and trying to avoid beef because it has a higher carbon intensity and things like this, I wouldn't be surprised if we start to see consumers making buying decisions based off carbon intensity. And what I am also seeing, starting with government regulation, is an increased awareness around the world of like carbon intensity and what that means, and people actually like wondering what is the carbon intensity of these products I'm buying, and that very naturally extends to fuels, which is a huge piece of anyone's carbon footprint who's driving around. So I think skyrocketing demand grows and grows and grows through 2050. I think for fleets, we're going to see it a lot because you can make a corporate decision where a lot of your, corporate emissions are coming from your fleet, and you can, bring your truck back, your package truck back to the facility to charge every night. Or for 18 wheelers, you can install a hydrogen network and you run the 18 wheeler along the same track where it has hydrogen. I think we're going to see that happen sooner. But consumers, I don't know how quickly consumers are going to get off gasoline globally. Like, definitely, if we go to California, you're going to see it happen more. But whenever you go to, developing countries, I don't know if we can hold them to the same expectations for decarbonization. Like, they need to move their products around too, and they might not have the luxury of a nationwide charging station network. So it's difficult to say for that one globally over the next couple of years.
And I think the implementation of some of these e-fuels is going to be mixed with existing fuel in some sort of percentage. Right now, you have biodiesels like 20% biodiesel,
Mm-hmm.
80% regular diesel. And I think we're probably going to see some of that as well as we're
A lot of
rolling
them
this
have
out.
blending standards that you have to follow.
Hmm. And maybe we'll get up to 100% at some point because I know, at least in the sustainable aviation space, there have been at least two 100% SAF flights across the Atlantic. So it's been proven that it can be done. Whether or not we're going to do it roll that out completely is another.
So, I mean, I think if I had a chance to just say one more thing, I'd like to end on this note. 10 years ago, the International Panel on Climate Change, said that we needed bold solutions to come to market, like technology that hadn't been invented yet, if we really wanted to, help mitigate the effects of climate change in the future. Syzygy has one of those bold solutions. We're one of those black swan type things that no one expected and no one really saw coming. And while things might seem challenging, and while it might seem like energy transition is struggling a little bit, I want to remind everyone that there are groups like Syzygy out there working on revolutionary things, and don't give up hope. We have a lot of things coming to market right now, and me being involved in it, being at like the tip of the spear in the fight of climate change, I am personally more excited about the future than I've ever been. It always gets hard when you start to do the real work, and I see the real work getting done every day. So, maybe end the rest of your day with a little hope.
Earthlings, consider your mental map expanded into new areas you can explore: nanoparticles, plasmonics, photoreactors, and that word that'll get you 25 points in Scrabble: syzygy. Way back in our first episode of the Earthlings podcast, Anna Ebers-Brow, who's a statistician and energy economist, had several scenarios of how climate change might play out based on how humanity might handle it. And one of those scenarios she called the dark horse scenario, which is where a new technology or event might come out of nowhere unexpectedly and help us turn back the worst effects of climate change. Anna predicted that it might be some form of AI. I'm reminded of this when I think of Syzygy, because perhaps they could be that dark horse Anna was predicting. Only time will tell. So keep your sensors pointed at Syzygy plasmonics, because I know we will. Our faith in humanity is restored this week by Laxman Singh, who, when he was 18, he came back to his home village of Lapodia, India, and discovered that his friends and family were suffering from acute water scarcity. Farming is the primary occupation there for 200 families, and drought, dilapidated infrastructure, and dry wells had cast a shadow on its agricultural viability. Laxman attempted to organize the village to repair the broken bund along the dry pond, but he was met with skepticism regarding feasibility and funding. Shocker. Where have we heard that story before? But he didn't give up. He set out to expand the pond himself and got a few friends to help him. By the end of the week, 20 villagers had joined the cause. And 2 months later, the monsoons came and the water filled up the pond for the first time in decades. Convinced, the village organized itself to continue the work, catalyzing Lapodia's journey towards prosperity. We honor Laxman for having a vision, taking a leadership role, and moving forward regardless of the haters to demonstrate to others a new future was possible on this beautiful blue green space flower that we call home.